Hey, so I'm Jennifer from the University of Cambridge, and I'm going to be talking a little bit about my work with Cotterell, where we used artificial languages to investigate inductive biases of neural language models. So natural languages are not all the same. If you were to have a look at a selection of the world's languages, you would see a huge amount of variation, lots of different linguistic features. For example, one that's quite easy to talk about is word order, so the order of the subject, object, and verb in a sentence. So most of the world's languages either use SOV, which is subject, object, verb order, like Japanese, or like English, use subject, verb, object order. But the other orders are all represented to some extent as well. So Irish, for example, uses VSO order, which is a little bit more rare. And given all of this variation, it would be quite useful to know whether language models have inductive biases that make certain types of language easier or harder to model. So for example, is it easier for a language model to model an SOV language or an SVO language? And it's particularly interesting, I think, given that so much of our NLP research is done on a small number of languages that share a lot of features. So it would be interesting to know whether certain types of language are easier or harder to model. But the issue is the neural architectures that we use for language modeling don't really offer a clear answer to these questions. So we've got to come up with a way to investigate the inductive biases. So what is the best way to investigate this? So let's say, for example, we want to investigate the word order and whether it has an effect on language model performance. So we could try evaluating language models on natural attested human languages that have different word orders and see if the language model performance changes across these languages. But if you take any two natural languages that have different word orders, they probably also differ in a lot of other ways. So maybe one has richer morphology than the other, maybe one marks case and the other one doesn't. And this is going to make it pretty difficult to say for sure that the differences in performance are because they've got different word orders rather than any of the other things that are different between them. So another approach that was taken by Vogel et al. Is to kind of take a natural language as a base, so say English, and then make changes to make versions of that language that have different word orders, different morphological properties, whatever you're trying to investigate, and then evaluate on those versions of the language. So the potential problem here is that it's quite difficult to be sure that your results aren't being influenced by the choice of base language. So certain constituent orders are kind of more commonly seen with some word orders. And so if you have an SVO language as your base, the other features of the language are probably best suited to an SVO language. So both of these are approaches that have a part to play in investigating the inductive biases of language models. Especially there's a trade-off between using the most natural and realistic language possible and experimental control. So in this work we decided to go for fully artificial languages, which maximizes the control that we have over the experiments. So using artificial languages, we can make sure that the languages we are investigating differ only in the thing we're investigating and not in any other way. We can also make sure that our corpora are perfectly matched. The sentences in the corpora differ only only by word ordering and nothing else, for example. So this approach allows for a really high degree of experimental control, which allows us to make stronger claims about how the features that we're investigating affect language model performance. So I'll talk a little bit about how we created the artificial languages that we used. So in this work, we investigated the effect of the head directionality of constituents on language model performance. So that does encompass the order of the subject, object, and verb in a sentence, but also the ordering of some of the other constituents. So for example, if an adjective comes before or after a noun in a noun phrase. So we started out by handcrafting a probabilistic context-free grammar. This was our base grammar, and all the productions here were head final. And then we marked the productions whose head directionality we could reverse. And so we call each of these marked productions a switch, so we can toggle it to be one way or the other. A switch value of 0 means that the head final ordering is what we're using, and a value of 1 indicates that it's the head initial ordering. So there were 6 of these switches, 6 swappable productions, which means that there were 64 possible ways to configure these switches, since they were binary switches. So we used the base grammar to generate all of our sentences, and then, as I'm going to demonstrate in a minute, we went through the sentences, swapping head directionality of the marked productions to get all 64 variants of the sentences. And as shorthand, I will talk about each grammar using the list of values of the 6 switches. So here you can see the productions that are marked with a switch. So these aren't the only rules in the grammar, just the switchable ones. These are kind of simplified generic versions of the rule because the real grammar also handled a couple of tenses, and it also had morphological agreement with the subject of a verb in number. So these are kind of the generic representations of the rules. So here we can see that we use the PCFG to generate trees for sentences in the artificial languages. So the configuration of switches that I'm showing here corresponds roughly to how the constituents are ordered in English. And the words for the language are taken from a list of phonotaxically plausible English nonce words. So if we want to flip one of these switches, we can do it pretty easily from the tree. So if we look at the second switch here, this corresponds to the rule which produces a transitive verb followed by an object noun phrase. And in this grammar, the switch is set to 1, which means that the object follows the verb, which is what we see in English. So these are the parts of the tree that this rule is concerned with. So if we flip this switch to a 0, we now want the object to come before the verb, which is the case in an SOV language like Japanese. So these two branches of the tree are going to get swapped around, and now we have the equivalent sentence for a different switch configuration. So what we do is we generate a tree for a sentence in a grammar with all switches set to 0, which is the base grammar, and then we permute branches like this to generate the equivalent sentence for all of the other grammars. And so this means that not only do the languages differ only in their word order, but it also allows us to have sentences that are matched perfectly across corpora. So we know that the differences aren't because of style or content of the sentences. And when we do statistical analysis, we can pair them up as being the same sentence. So our experiments, once we have our 64 parallel artificial language corpora, we use them to train and evaluate language models. In this case, we tested both LSTM and transformer-based models. So for each grammar, we had 100,000 sentences, which were split into 10 splits, each of which was then divided into train, test, and dev sets in an 8-10-10 split. And at all points, the corpora are fully parallel between different languages. So the sentences in the train split, in each split, are exactly the same across all languages up to changes in the ordering of the words. So here are the average perplexities on the combined test sets for each of the artificial languages, with the LSTM model results in orange and transformers in blue. And the first thing you notice looking at this is the LSTMs have got pretty consistent performance across all of the configurations of the switches. They seem to be pretty much agnostic to the changes in word ordering. The transformers, on the other hand, do vary quite a bit across grammars. So the first thing is that it's interesting to remark that the two architectures do seem to be affected differently by the differing word orders. So we go on to do a little bit of analysis. So one thing we look at is that in attested human languages, some word orders are more common than others. And it's not completely clear why this may be, but some have suggested that human cognitive biases may make some word orders easier to learn than others, which may contribute to the non-uniform distribution. And we wondered whether neural language models would perform better on more commonly attested word orders, which might suggest that the biases are similar to those that are theorized in humans. So our switch mechanisms, the way they were written, allowed for the creation of artificial languages that had overall word orders of SOV, SVO, OVS, and VOS. And so here we can see the performance of the language models on these subgroups of languages, along with the distribution of those orders among attested human languages. And we can see the performance doesn't correlate at all really with how commonly seen these orders are. And in fact, the transformer achieves its best performance on languages with VOS order, which is a very rare order among human languages. So that's quite interesting to note. So we also wanted to take a closer look at the effects of each switch in the grammar on the performance, as well as the effects of first order interactions between switches. So that's like, if the first two switches are both on. So to do this, we used a mixed effects model to model the perplexity of each sentence as a function of the switches in the language it belongs to. So we used a mixed effects model because the perplexity for each sentence is going to vary naturally, with some sentences being more difficult than others. And so if we group parallel sentences across languages together, we can account for that quite nicely and just look at the effects of the switches. So the mixed effect model calculates a coefficient for each switch and for each switch-switch interaction. So contrast coding was used. So basically, when we're looking at the first order interaction coefficients, that is looking at the effect of a shared head directionality. So for those two switches being the same. And a negative coefficient basically indicates that shared head directionality improves performance. And so we can see, looking at the LSTM, that none of these values are large, which indicates that no switch or switch pair has a particularly notable effect on performance, which is pretty much what we saw looking at the perplexity results. And the coefficients calculated for the transformer don't really show any kind of easily explainable pattern. There's nothing that really stands out as having a reasonable explanation. So there are a few avenues for future work on this topic. So one possibility is to repeat our experiments with a different base grammar. The base grammar we used was quite simple, and inevitably some of the choices about the design are kind of arbitrary. So repeating the experiments with a different, richer grammar would help to validate the results. Another option would be to extend the work to investigate typological features, beyond word order. So, for example, you create artificial languages with different systems of morphology with varying levels of richness. And finally, tuning the probabilities of the PCFG in our work was done by hand. And so the method could be improved if you could develop an automated method for setting the probabilities. So in summary, our paper makes the case that artificial languages are useful for investigating inductive biases of neural language models because they offer a high control setting for experiments. We use this method to investigate the effects of head directionality of constituents on language model performance, and we find that LSTMs and transformers don't have the same inductive biases. We find that the LSTM doesn't really seem to show a clear preference in terms of head directionality on these constituents, and the preference that transformers show doesn't really seem to resemble anything that we see in the distribution of attested languages. We'd really like to see more work in the future using this method with artificial languages to investigate inductive biases concerning other typological features.